Namaste and welcome to the Deep Dive. Today, we're taking a closer look at something so fundamental, so constant that we barely give it a second thought: motion. It's happening all around us, every single moment. Yet understanding its true nature can reveal some truly surprising insights.
Indeed. And we've gathered a really fascinating collection of questions and answers to guide us.
Think of them as clues, maybe? Helping us peel back the layers of how everything moves, from the air we breathe to uh, satellites orbiting our planet.
Exactly. Our goal isn't just to rattle off definitions, you see. It's to truly unpack why things move the way they do. We want to connect those fundamental principles to the world you experience every day. Get ready to maybe challenge some of your intuitive ideas about movement.
Okay, let's jump right in then. Let's see the world through a new lens.
The illusions of movement. What do we really see?
We talk about things moving, but it's often more about inference than direct observation, isn't it? Take the air, for instance. You can't actually see air, so how do you know it's moving?
That's a great starting point, actually, for understanding how our senses work with physics. We infer air's motion by observing its effects on other objects. Think about it, yeah. You see dust swirling or the leaves on a tree dancing, and immediately you understand there's a breeze.
Oh, okay.
We're watching the consequences of motion, basically.
That makes perfect sense. We're kind of like detectives, constantly piecing together clues. And speaking of observations, here's where motion itself can play a bit of a trick on us. Imagine you're on a bus, right, speeding down a busy highway. What happens to the trees and buildings by the roadside?
Well, for you as the passenger, those objects outside don't rush past in the same direction you're going. No. Instead, they appear to recede, moving backwards relative to your position. It's a classic example, really, of how our perception shifts with our own movement.
Right. And this isn't just a quirky visual effect, is it? It hints at something much deeper about how we describe motion.
Absolutely. This kind of everyday observation, like how the bus appears to move for someone standing on the roadside, but for you inside, well, it feels completely stationary relative to your seat. It reveals a fundamental truth. An object's motion is relative. It may appear to be moving for one person and stationary for another. There's no absolute universal stationary point, you see. It all depends on your reference, your point of view.
Pinpointing your position, where does the journey begin?
Okay, so if everything is relative, how do we ever measure anything consistently? If I'm trying to tell you where something is or how fast it's going, I can't just say it's moving. I need a rock-solid starting point, don't I? A fixed reference.
Exactly. To describe the position of an object precisely, we need to specify a common ground, a reference point. It's often called the origin. Without that anchor, any description of position or movement becomes, well, pretty much meaningless.
Right.
It's like trying to give directions without saying, start from the big temple or something.
Yeah, okay. And in physics, especially when we start with the simplest forms of movement, this origin becomes our universal anchor. It makes perfect sense to simplify things first, right? Get the basics down.
Precisely. That's why, in our initial studies, we often begin by describing motion along a straight line. It's the most straightforward path you can take. And when an object begins its journey from a point O on that line, O serves as its essential reference point. It gives us a consistent baseline for all our measurements, you see.
It's quite incredible how we've gone from just, observing motion to understanding it so deeply that we can actually harness it. I'm reminded of something from our sources. Among the many examples of controlled motion, the generation of hydroelectric power really stands out.
Right.
It's a powerful reminder that by understanding these principles, we can turn the raw energy of flowing water into electricity, literally illuminating our lives. It's quite something.
The path less traveled, or just the shortest route.
Hmm.
Distance versus displacement.
Okay, now that we have a starting point, let's trace the journey itself. We all intuitively understand distance as, how far we've gone, but in physics, we often need to be more precise about what kind of far. And that's where the crucial distinction between distance and something called displacement comes in.
You've hit on a critical point there. Distance is simply the total path length an object covers, regardless of its twists and turns.
Yeah.
Think of it like your car's odometer.
Yeah.
It just keeps adding up every meter you travel. Simple as that.
But then we have displacement, which focuses only on where you started and where you ended up, almost ignoring the journey in between.
Precisely. Displacement is defined as the shortest distance measured directly from the initial to the final position of an object. It's the straight line path, basically. It's not just about how far, but also in what direction. That's key.
This is where it gets really fascinating. you can actually have zero displacement, even if you've walked for miles. How can that be?
It's a concept that often surprises people, but it's absolutely true. The magnitude of displacement can be zero, even if you've covered a significant distance. This happens if the object, after all its movement, simply returns to its initial position.
Ah, like a round trip.
Exactly. Imagine a round trip to the market and back home. Your odometer might show 10 kilometers, but your displacement from your starting point is exactly zero. You're back where you began.
Wow. That makes it a fundamentally different concept then. Distance is just a numerical value. Its magnitude like 10 kilometers. It doesn't care about direction at all.
And that's the key difference. Distance is what we call a scalar quantity. It only has magnitude. But displacement is a vector quantity.
Vector. Right.
It has both magnitude and direction. Saying you've displaced 5 kilometers isn't enough. You need to say 5 kilometers north or 5 kilometers towards the east. That direction tells us exactly where you finished relative to where you began.
Let's try and illustrate this with a classic scenario to make it really crystal clear. Imagine an object moving from a point O. It travels 60 kilometers to a point A.
Okay, got it. 60 kilometers to A.
Then it turns back along the same path and stops at a point B, which is 35 kilometers from the original starting point O. First, what's the total distance covered?
All right, let's break it down. So from O to A is 60 kilometers, straightforward. To get from A back to B, which is 35 kilometers from O, the object must have traveled an additional, 60 minus 35. That's 25 kilometers back towards O.
Right.
So the total distance covered is the 60 kilometers going out plus the 25 kilometers coming back. That gives us 85 kilometers, a significant journey.
Okay, 85 kilometers total distance. Now, for the same scenario, what is the magnitude of the displacement?
Displacement. Now we only care about the straight line distance from the initial position O to the final position B. So irrespective of the path taken, the point B is 35 kilometers from O. That's it. The magnitude of the displacement is simply 35 kilometers.
Wow, 85 kilometers distance, but only 35 kilometers displacement. See how different that is?
Exactly.
That distinction is truly critical for understanding motion. And thinking of journeys, our car's odometer is a perfect example of measuring distance, isn't it?
Spot on.
It just adds up every kilometer you travel, caring only about the total ground covered, not whether you ended up back where you started.
The rhythm of movement, uniformity, speed, and velocity.
So we can measure the path and the net change in position, distance and displacement. Got it. But how do we describe how something moves? Sometimes it's smooth and steady, other times it's, well, erratic. If an object covers equal distances in equal intervals of time, what do we call that kind of motion?
That predictable, steady movement is what we term uniform motion. Picture a train traveling at a perfectly constant speed on a perfectly straight track. It's consistent, unwavering.
And the opposite of that, when things aren't so smooth, is non-uniform motion. Our sources give a great example. A car inching its way through a crowded street.
Oh yes, definitely non-uniform.
It's constantly speeding up, slowing down, stopping, definitely not covering equal distances and equal times.
Exactly. And the most common way we quantify this rate of motion is, of course, with speed. It's simply the distance traveled by an object in a unit of time. How much ground you cover per second or per hour.
So if you're finding out the distance an object travels in, say, 1 second, you're essentially measuring its speed. And the standard international unit for speed, the SI unit, which scientists worldwide agree upon, is meters per second, right? Written as MS1.
Correct. Meters per second.
And for an entire trip, especially one with all those stops and starts like that car in traffic, we often talk about average speed. How do we calculate that?
The average speed of an object is quite straightforward. You simply divide the total distance traveled by the total time taken. It gives you an overall rate for the entire journey, smoothing out all the little variations along the way. But here's an interesting point. While speed tells us how fast, it doesn't tell us where that speed is taking us. For that, we need velocity. Velocity is a quantity that specifies both the speed of an object and its direction of motion.
Speed with direction.
Exactly. Speed with a compass attached, you could say.
So if velocity includes direction, that means, wait, we can actually change an object's velocity without even changing its speed. That sounds counterintuitive to our everyday experience.
It's one of those key aha moments in physics, isn't it?
Absolutely. The velocity of an object can change in 3 ways. By changing its speed, by changing its direction of motion, or by changing both.
Right.
So yes, you can keep the same speed, say 60 kilometers, but if you simply turn a corner, your velocity has changed because your direction is now different.
Right. And just like average speed, we have average velocity. Our sources explain that if the velocity of an object is changing at a uniform rate, the average velocity is calculated as the arithmetic mean of its initial and final velocities.
That's right. A neat trick for consistently changing motion. Add the start and end velocities, divide by 2.
And importantly, both speed and velocity share the same SI units.
Yeah.
ms1, meters per second.
Correct. Units are the same, but the meaning is very different.
Let's put this into practice with a real-world puzzle, one that might even trick a seasoned swimmer. Imagine Usha swimming laps in a 90-meter pool. She powers from one end to the other and back again, covering a total of 180 meters in just 1 minute.
Okay, 180 meters in 60 seconds. Got it. Now, here's the kicker for our brains. What would her average velocity be for that minute?
This is a perfect test of that distance versus displacement, speed versus velocity distinction. Since Usha starts at one end and returns to the exact same end, her final position is identical to her initial position.
Meaning?
Meaning her displacement is 0. Nada. Zilch.
Right.
And because average velocity is displacement divided by time, her average velocity for that minute is 0 meter s1.
Amazing. She put in all that effort, covered all that distance, 180 meters, but her net velocity is 0. So what about her average speed for the same swim? That must be different.
Oh, yes. For her average speed, we take the total distance covered, which is 180 meters, and divide it by the total time taken, which is 1 minute or 60 seconds. So 180 meters divided by 60 seconds gives her an average speed of 3 meters s1.
Okay, 3 meters speed, 0 meters velocity.
It really highlights how crucial that direction component is for velocity, doesn't it?
The push and pull understanding acceleration.
Okay, so we know velocity can change. It can change speed, change direction, or both. But what do we call that rate of change of velocity over time? We need a term for when things speed up, slow down, or simply change direction.
That's where acceleration comes in. It's the physical quantity introduced precisely to measure the change in velocity of an object per unit time, how quickly velocity changes.
And this concept has its own precise SI unit, doesn't it? It's not just meters per second.
It does. The SI unit of acceleration is meters per second squared, or ms2, meters per second.
Right.
And remember, acceleration isn't just about speeding up. That's a common misconception. It's any change in velocity.
Any change.
Yes. When acceleration is in the same direction as the velocity, it's taken as positive the object is speeding up. If it's in the opposite direction, it's negative, meaning the object is slowing down. We often call that deceleration, but it's technically negative acceleration. And changing direction, even at constant speed, is also acceleration.
Got it. And uniform acceleration means a consistent change in velocity over time.
Right,
like a classic example of a freely falling object.
Exactly. Due to gravity, neglecting air resistance, it speeds up downwards at a very constant rate. That's uniform acceleration.
Conversely, what if the motion is uniform? If an object is moving at a uniform velocity along a straight line.
Then there's no change in its velocity for any time interval. Constant speed, constant direction.
So it's acceleration.
Must be 0. No speeding up, no slowing down, no turning. Acceleration is nil.
Okay, let's apply these ideas to a couple of practical scenarios. First, a road trip. An automobile's odometer reads 2,000 kilometers at the start and 2,400 kilometers at the end of an 8-hour trip. What was the car's average speed in kilometers per hour?
Okay, straightforward average speed calculation. The total distance traveled is 2,400 kilometers minus 2,000 kilometers, which is 400 kilometers.
So the trip took 8 hours.
So the average speed is simply 400 kilometers divided by 8 hours, which gives us a neat 50 kilometers per hour, 50 kilometers per hour.
Simple enough. Now, let's picture Rahul on his bicycle, starting from a stationary position, completely still. He paddles to attain a velocity of 6 meters s1 in 30 seconds. What is his acceleration during this initial burst?
Okay, so he starts from rest, meaning his initial velocity, u, is 0 meter as in s1. His final velocity, v, is 6 meters 1, and the time taken, t, is 30 seconds. Acceleration a is the change in velocity divided by time, so a vut.
6030.
Exactly, which is 6 divided by 30, or 15, which equals 0.2 meters is 2. A decent push.
Okay, 0.2 meters squared. And what if Rahul then applies the brakes? After attaining that 6 meters 1, he applies the brakes, and the bicycle's velocity comes down to 4 meters 1 in the next 5 seconds. What is the acceleration in this second case?
Right, new scenario. Now, his initial velocity for this part is 60 meters s1. His final velocity is 4 meter s1, and the time interval is 5 seconds. So the acceleration is a vut equals 465.
That's 9 s2 divided by 5.
Which gives us 9.4 meters s2.
That negative sign, that's so important there, isn't it?
Crucial. It indicates deceleration or acceleration in the opposite direction to his motion. He's clearly slowing down.
Painting pictures of motion graphs as guides.
Numbers and formulas give us precision, definitely. But sometimes a visual representation, a graph, helps us understand the whole story of motion at a glance. How do we chart motion effectively using graphs? When we draw a distance-time graph, which axis typically represents time.
Ah, graphs. Very useful. When plotting motion, time is almost universally represented on the x-axis, the horizontal axis. It's our independent variable, ticking along steadily, forming the foundation of our observations. Distance or position usually goes on the y-axis, the vertical one.
Okay, time on the horizontal. And what those lines on the graph tell us is incredibly insightful. For an object moving at a uniform speed, for instance, what does a graph of distance traveled against time look like?
For uniform speed, where equal distances are covered in equal times, a graph of distance traveled against time will always be a straight line, starting from the origin and going upwards diagonally.
A straight line, consistent progress.
Exactly. It's a clean, consistent progression that's easy to read.
And we can actually extract the speed directly from that line, can't we?
Yes, you can. The speed of the object is determined from a distance-time graph by finding the slope, or the gradient, of that line.
Slope equals speed.
Correct. A steeper slope means a higher speed. A flatter slope, a slower speed.
So if the line isn't straight on a distance-time graph, if it curves, what does that immediately tell us?
A nonlinear distance-time graph, a curve, is a clear indicator of non-uniform speed. The object is either speeding up, curve gets steeper, or slowing down, curve gets flatter. It's not covering equal distances in equal time intervals.
Okay, so distance-time graphs reveal speed through their slope. What about velocity-time graphs? They must show something different. If an object moves at a uniform velocity, what does its velocity-time graph look like?
Velocity-time graphs. For uniform velocity, constant speed, and constant direction, the velocity of time graph will be a straight, horizontal line. Yes, parallel to the x-axis, the time axis. This visually confirms that the velocity remains constant no matter how much time passes. The value on the axis doesn't change. And the area enclosed by that graph tells us something else very important.
The area.
Yes. For an object moving with uniform velocity, the area enclosed by its velocity time graph and the time axis actually represents the magnitude of the displacement of the object during that time interval. Velocity multiplied by time gives displacement.
Interesting, okay. And for any uniformly accelerated motion where the velocity is changing steadily, the velocity-time graph will also be a straight line, just not horizontal, right?
Exactly. For all uniformly accelerated motion, the velocity time graph is a straight line, but it will have a slope. It will be diagonal. The slope of that line, the velocity time line, would then give you the acceleration. Constant slope means constant acceleration.
And once again, the area under this type of graph gives us crucial information. Our sources confirm that the distance moved by an object in a given interval of time can be determined from its velocity time graph. Piece of tau.
Again, simply by calculating the area under the velocity time graph for that interval. Whether it's uniform velocity or uniform acceleration, the area under the VT graph gives you the displacement or distance traveled.
So area under VT graph is displacement distance. Got it.
But be careful. Just like before, a nonlinear velocity time graph indicates an even more complex scenario. A curve on a VT graph.
Means.
It represents non-uniformly accelerated motion. The acceleration itself is changing over time. Think of a roller coaster that's not just speeding up, but speeding up faster and faster, or inconsistently. The slope itself is changing.
The formula for movement equations of motion.
Okay, we've observed, defined, and graphed motion. Now, the really powerful part, can we predict it? We have some incredibly useful equations for that, don't we?
Right.
Tools to forecast exactly how an object will move, at least under certain conditions. Which equation, for example, relates velocity acceleration and time for an object moving with uniform acceleration? The first big one.
Ah, yes, the equations of motion. The first one, a fundamental one, is v equals u plus at. Here, v is the final velocity, u is the initial velocity, a is the constant acceleration, and t is the time elapsed. It's the simplest way to see how velocity changes over time.
VE plus h. Okay. And how about the equation that tells us about an object's position, its displacement as, over time, again for uniform acceleration?
For the position-time relationship, we use the second equation, s equals u plus half at 2. Here, s is the displacement, u is the initial velocity, t is time, and a is the uniform acceleration. It helps us calculate how far something has moved in a certain time.
S plus half it squared.
Got it.
And finally, there's a third equation that neatly connects position and velocity without needing to know the time taken. The equation 2 equals v2 u2 represents the relation between which quantities?
That third equation, 2s is v2u2, specifically relates position and velocity along with acceleration. It's incredibly useful when time isn't known or needed in your calculation. Position-velocity relation.
Okay, those three are like the holy trinity of kinematics.
Haha, you could say that. What's truly powerful about these three equations is their versatility. They are fundamental tools for analyzing and predicting motion. However, and this is really important, they come with a very strict condition for their applicability. The object must move with uniform acceleration.
Only for uniform acceleration.
Yes. If the acceleration is changing, these equations won't give you accurate results. You need calculus then, usually.
That's a crucial detail to remember. Let's see them in action with a train example. A train starting from rest attains a velocity of 72 km/h+1 in 5 minutes. Assuming uniform acceleration, what is its acceleration?
Okay, first things first, units. We need SI units, meters and seconds. 72 kilometer needs converting. That's 72 times 1,000 meters divided by 3,600 seconds, which comes out to 20 meters.
20 meters in 5 minutes.
5 minutes is 5 times 60, so 300 seconds. Since it starts from rest, initial velocity u is 0 meters, final velocity v is 20 meters, and time t is 300s. We can use the first equation, v u plus at. So 20 plus of I multiplied by 300. Solving for a, we get as 2,300, which simplifies down to 115 meters, just 2.
115 meters squared. Okay. And another one. A car accelerating from one speed to another. A car accelerates uniformly from 18 km/h+1 to 36 km/h+1 in 5 seconds. What's the distance covered by the car in that time?
Right. Again, unit conversion's key. 18 kilometers is half of 36 kilometers. So if 36 kilometers is 10 meters, then 18 kilometers must be 5 meters.
Good shortcut. So u of 5 meters, v equal error is 10 meters, t equals 5. We need distance s.
We can first find the acceleration using a v gush 2. So a equals 8.1555 plus 1 meters 2.
So acceleration is 1 meter 2. Now for distance.
Now we can use the second equation. S equals 1/2 at 2. Plugging in the values. S at 5 multiplied by 5 plus arrows 0.5 multiplied by 1 multiplied by 5 squared. So S equals 25 plus 0.5 times 1 times 25 plus 12.5.
Which gives us 37.5 meters.
Exactly. The car covered 37.5 meters in those 5 seconds.
These equations truly are the bedrock of understanding predictable motion. They allow us to calculate and foresee the world around us with incredible precision.
The circular dance motion without changing speed.
Okay, we've talked a lot about acceleration, meaning a change in speed, speeding up, slowing down. But here's a surprising twist, one of those real aha moments we talked about.
Right.
Can an object accelerate even if its speed stays exactly the same? Constant speed, but still accelerating.
Yes, absolutely. It loops back to the definition. When the velocity of an object changes, the object is, by definition, accelerating.
Velocity changes.
And the key is velocity includes direction. So an object can accelerate even if the magnitude of its velocity, its speed, does not change. This happens due to a continuous change in its direction of motion.
Wow. Okay, this makes me wonder, how can direction alone cause acceleration? Imagine a journey that just keeps curving, never going in a straight line.
Think about a polygon, like a hexagon or an octagon, used as a racetrack. Athletes running on it change direction at each corner, right?
Yes, sharp turns.
Now imagine increasing the number of sides of that track indefinitely. Make it a 100-sided polygon, a 1,000-sided one. What shape does the track ultimately approach?
It'll get smoother and smoother. It looked like a circle.
Exactly, a perfect circle. This helps us visualize how constant small changes in direction occurring continuously lead to motion along a circular path.
So an athlete running on a perfectly circular track at a constant speed, say 10 meters the whole way around, is technically accelerating. That definitely feels counterintuitive to our everyday idea of speeding up.
It does, but it's physically accurate. If an athlete moves with a velocity of constant magnitude, constant speed, along a circular path, the only thing changing from moment to moment is the direction of their velocity vector. Because velocity is a vector and its direction is continuously changing, the athlete is, indeed, accelerating. The acceleration is directed towards the center of the circle, actually.
Towards the center. Okay, so this is the clear example of accelerated motion, even with constant speed.
Precisely.
And we have a name to this, don't we? The motion of an object when it moves in a circular path with uniform speed is called
uniform circular motion. Uniform speed, circular path.
Right. And there's a simple formula to calculate that constant speed, is there?
Yeah. Yes. If an athlete takes seconds to go once around a circular path of radius r, their speed is given by v equals to 2rt.
Circumference over time.
Exactly. Just the total distance, the circumference 2πr, divided by the time taken for one full lap, d.
Makes sense. Now, what happens if that athlete, or maybe a stone tied to a thread and swung in a circular path, suddenly lets go? or the thread breaks, does it keep going in a circle for a bit?
Ah, good question. No, it won't. The moment the constraint, the pull of the thread, or the athlete choosing the path is removed. When a stone tied to a thread and moved in a circular path is released, it moves along a straight line tangential to the circular path at the exact point of release.
Tangential, like skimming the edge.
Exactly. It wants to continue in a straight line due to inertia, its tendency to resist changes in motion. The string was constantly pulling it inwards, forcing the change in direction. Once that force is gone, it simply follows the direction it was headed at that precise instant, which is tangent to the circle.
A perfect demonstration of inertia in action. And we see this phenomenon on a grand scale every single day, don't we? Our sources give a perfect example of uniform circular motion. A satellite in a circular orbit around the Earth.
Yes, a classic example. Assuming a circular orbit, it maintains a relatively constant speed, but its direction is continuously changing as it curves around the Earth. This means it's constantly accelerating towards the Earth due to gravity, and that acceleration is what keeps it in its beautiful, endless dance, preventing it from flying off in a straight line into space. Outro.
Wow. What an incredible journey we've taken through the universe of motion today. Really unpacked a lot. From those first subtle clues that tell us air is moving, all the way to the critical differences between distance and displacement, speed and velocity.
And the dynamic forces of acceleration, understanding graphs.
And even the elegant, always changing path of uniform circular motion where constant speed still means acceleration.
We started with what seemed like pretty simple observations, didn't we? But by meticulously unpacking each concept, using those questions as guides, we've hopefully built a more powerful framework for understanding how everything around us moves.
Yeah.
It's a profound testament, really, to how careful observation and precise definitions lay the foundation for all scientific understanding. It reveals a deeper beauty in the mundane, everyday movements we see.
You've just taken a deep dive into the very fabric of movement, piece by piece, concept by concept. Hopefully it makes you look at the world a little differently now. So consider this as we wrap up. If all motion is relative, as we established right at the start, and even a satellite in a supposedly perfect circular orbit is constantly accelerating, what does that imply about our own perception of stillness right here on a rotating, orbiting Earth?
Interesting thought.
Is anything truly motionless? Or are we always, constantly in a state of complex, multi-directional acceleration, even when we feel perfectly still?
Something to ponder, definitely.
Something to ponder until our next deep dive.